Welcome everybody. Thanks for being here for the CITA seminar. We're very pleased to have Margot Mandy with us today. Margot is professor of chemistry at the University of Northern British Columbia. She received her PhD in theoretical chemistry from the University of Toronto and has a long-standing connection to CITA. She's an expert on kinetic modeling of reaction networks for atmospheric chemistry and the interstellar medium. And today she'll be telling us about her work on molecular hydrogen in collisions. So thank you, Professor Mandy. Please take it away.
Okay, thank you very much. Molecular hydrogen in collisions, that's kind of been the story of my career. The thumbnail sketch is for my master's, I did helium H2. For my PhD, I did H and H2. And now I'll be working on H2 plus H2, which is a much, much bigger problem. I realize in conversation that a lot of people have not heard of the University of Northern British Columbia. It's a fairly new university. It was officially opened by the Queen 29 years ago last week. And I have to say it's been an adventure. Aside from the PhD in my field, I feel the best prep I had was my time as a leader at Goian. What you have, what you don't have, you can't count on getting. They have arrived, make it work. So we're fairly small. Our head count is about 4,000 students with about 2,800 full-time equivalents. That's a reflection of how the Canada Student Loan Program does not work terribly well in Northern BC. About 10% of our students are international, and most of those are graduate students. We're located in Prince George. When I first arrived there in '94, I was handed a brochure by the Chamber of Commerce, which made the claim that Prince George was centrally located. Basically, you have to go 750 or 800 kilometers to get to anywhere bigger. We're not on the coast. That's another 720 kilometers to the west. That stretch of highway is known as the Highway of Tears. That's had a lot of media coverage about Indigenous issues. We have a large Indigenous student population, and unlike other parts of Canada, many of the First Nations in Northern BC do not have treaties, and they know who they are, and they know their relationship to the land, and that plays out in interesting ways in resource development. Okay. Hydrogen molecule, simplest one going. It's got 2 protons, 2 electrons, and it's got 1 sigma bond. It's one of the systems that is tractable from a viewpoint of doing calculations based on theory. So it's possible to, test theory against experiments. And when I first started working in this, and this was the era of computer cards, experimentalists tend to be kind of dismissive of theoreticians and computational people. Oh, you guys are just like models. That has evolved. More about that later. The very first study of a collision of H2 with a hydrogen atom was simulated in the 1930s by hand. London, Iron, Polanyi, and Sato had developed a model potential energy surface. This is Michael Polanyi, the father of John Polanyi, and brother of Carl Polanyi, both of them got Nobel Prizes. Anyway, this is a model potential. It was kind of like proof of concept. I mean, this is barely a decade after sort of like the quantum crisis. They used a classical trajectory calculated by hand. And what they found was it was bouncing around at a local minimum. And that was totally unphysical. We knew that later. But it was a very important proof of concept. It would take 2 or 3 more decades before the computers caught up. And that's also been part of the whole business of theoretical and computational chemistry. The computers catch up. Basically, by the time we figure out how to do it, we just have to wait for the computers, and then we move forward. Early potential energy surfaces were models. Now, to study a collision, you need a potential energy surface because the gradients on that surface are what gives you your forces. The Leibniz potential is still out there. It's used as a few parameter model potential, and it's used for a wide range of chemical systems. So a lot of people will do initial exploration with a rather crude model surface and then decide whether they need a better one. It does allow for some qualitative conclusions, but don't trust the numbers. Okay, more accurate potentials. Well, you get the points on your potential with rigorous ab initio quantum calculations. You basically have a confirmation of molecules or atoms, and then you basically solve the Schrodinger equation. And of course, you have to use approximation methods, and the real sticky part is the interaction of electrons with electrons. So there's a number of approximation methods, some of which limit the validity, but the limit is being pushed all the time. We're getting better and better calculations. So in the 1970s, we had potentials that were deemed chemically accurate because they predicted the right outcome of a collision, whether a reaction would occur or not occur. More recent potentials are spectroscopically accurate. You know, they are accurate to within a few wave numbers. So this is great, but we still have a ways to go. So a brief history of H2, and Peter Martin just sent me a paper this morning, which I didn't quite finish reading before I came down. But in the 60s, there was a quantum calculation, and it was state-of-the-art for its day, by Kolos and Wolowitz, to calculate all the energy levels of the ground state hydrogen molecule with improved access to computational resources. They did an improved calculation. And the significance of that calculation was they had to turn to the spectroscopist and say, look again. And Hertzberg actually had to revise the experimentally determined dissociation energy for H2. Hertzberg systematically studied the spectra of atoms, diatoms, and small polyatomics. And that work has certainly stood the test of time. The work by Kolos and Wolowitz included adiabatic and non-adiabatic and relativistic effects. When I say adiabatic, that means that the potential is associated with one electronic state. A non-adiabatic potential involves crossing with another electronic state. So sometimes you have to have these corrections. And that laid the groundwork for the calculation of Turner, Kirby-Dokin, and D'Argano of the quadrupole emission probabilities. And those are actually quite important in interstellar hydrogen. We tend to ignore them in terrestrial chemistry because the probability is so low. But when we get to the densities characteristics of the interstellar medium, we need to allow for that quadrupole emission because it can compete effectively with collisions in certain density regimes. So here's all our VJ states of the hydrogen molecule. And our vertical axis, in this case, is the energy of millihartrees. And our horizontal axis is the rotational quantum state. So you can think of these as sort of families of, or manifolds of states. So V equals 0, you could go up to J equals 37. That state is actually above the dissociation limit. That is, this group is, the horizontal dotted line is the dissociation limit. If you want to make a hydrogen molecule fall apart, that's how much energy you got to get into it. That group of states above that line are known as quasi-bound. That means that they have a probability of tunneling to dissociation. And again, at low densities, that can compete with collisions. So there's a whole body of literature in the 70s where they talked about bound type quasi-bound and unbound quasi-bound. We don't make that distinction so much in interstellar chemistry. We look at the actual density effects, but we know those tunneling probabilities. Now, the quadrupole emission has a selection rule of delta J equal plus or minus 2 or 0, and it must be exoaeric, it must go down in energy. And so in this particular case, these are all the quadrupole emissions that are possible from state 7-4. What happens with molecular hydrogen is if it gets excited to a higher state by collisions, then you've got to figure out, is it going to radiate down to the ground state, or is it going to undergo another collision? And if it undergoes another collision, where does it go? Well, that depends a lot on what it is hit by. So we've considered 3 colliders: helium, the hydrogen atom, and the hydrogen molecule. Now, molecular dynamics, reaction dynamics, people love these systems because they're small. And because they're small, they're tractable, we can do fairly good ab initio calculations, and we can even do some quantum calculations of colliding systems if the energy is low enough. Those calculations are usually restricted to states, VJ states that have less than 1 electron volt. Well, that's only a handful of states. That's not even a quarter of the way to the dissociation limit. So we're not going to be able to get all our transition probabilities from quantum calculations. We have to use other methods. More about that later. The reason we need all of them is that hydrogen gas in an interstellar shock is not at equilibrium. So we need all the details of that 348 VJ states if we want to do a decent model of a shock. Well, in order to get decent numbers, we need decent potentials. Helium H2, when I was a master's student, I used the surface of Wilson, Capral, and Burns, which was state-of-the-art for its day. That was about 200 points. There were a few other potentials out there, but they were limited to restricted geometries, almost always collinear. Sometimes very small separations between the helium and the hydrogen. Wasn't really a good characterization of van der Waals minimum. And most of them were small, were fine if you had the helium and H2 really close, but not at large separations. Well, we want to dissociate hydrogen molecules. We need large separations. So the Wilson, Capral, and Burns surface did allow for that, but there was a problem. We knew it had a hole in the repulsive wall, and every now and again we would, simulating a collision, and we'd have it disappear down the hole. That was my master's. It was a really good week if I got 1,000 trajectories. I was lugging computer cards from the chemistry building next door down to the engineering annex. Now there was a new surface by Boothroyd, Martin, and Peterson, and my graduate student repeated on that surface the calculation I'd done for my master's in an afternoon. Computing power now is really great. Okay, HH2, well, we had that left surface. We knew it was unphysical. In the 60s, Porter and Karplus used quantum calculations, but they basically used it to set the parameters on a left-style surface. A left-style surface only has a few parameters with the result that it's very stiff. The first decent potential came out in 73, but it was only for collinear H plus H2, and there was 111 ab initio points. The thinking in reaction and molecular dynamics then was, okay, let's sort this out for the collinear case, and then we can infer things about the full dimensional case. That didn't work out. A few years later, we got a full three-dimensional surface with 156 more ab initio points. So these were non-linear conformations of the three atoms. And that was published. The next paper in the journal was Truller and Horowitz's fit for this. And so that was actually the surface that I did my PhD on. Meanwhile, we want to move on. We want to move on to H2H2. And there were no decent H2H2 potentials. So eventually, Peter Martin, in connection with Arnold Boothroyd, Bill Keogh, and Mike Peterson, decided to see if they could do it. And of course, once you start working on an H2H2 potential, you just have to pull one of those hydrogen atoms way far away, and it reduces to an H3 potential. So in the course of their quest for the H2H2 potential, they generated an improved H3 potential. So, now we're getting into almost 10,000 points. This was huge progress. So the H2H2 surface, nobody in the molecular dynamics community seemed to be terribly interested in a global surface. They're interested in things like pressure broadening, where hydrogen molecules would hit each other and sort of distort each other a bit and move around the energy levels a bit, which led to, broadening of the lines in the spectrum. Well, that only involves a very small part of the potential. What we needed to do the stuff we're interested in was the full deal. We need to be able to have two hydrogen molecules hit each other, exchange, dissociate, doubly dissociate, whatever. We needed a potential that would describe that. So Peter Martin and colleagues did it. They published the points first. A Spanish group of Eduardo Suarez and Penalba fitted it, but they sacrificed some of the goodness of fit to use some functional forms that were really convenient for quantum calculations. Quantum calculations are computationally very intensive, and it's nice if you can do angular parts of your wave function analytically rather than numerically. So they were catering to that community. Meanwhile, more points were added, so we're up to close to 50,000 points. And previous potentials that were out there, they kind of, they were mainly for restricted conformations. They weren't the full deal. The initial results when quantum calculations started to come forward was that there may be a problem with the BKMP2 H2H potential because of the anisotropy. There's certain integrals and scattering calculations that should go to zero. They don't for the BKMP2 surface. And then there's a more recent potential, which is kind of regarded as state-of-the-art. Quantum calculations done on that one agree fairly well with experiment, like cross-beam experiments and that sort of thing. It was touted as global, but it turns out it's not. It kind of craps out about 2/3 of the way up to the dissociation limit. And that has to do with the ab initio technique that was used to calculate it, electrons have to belong very clearly to some nuclei and not other nuclei. So that seems to be the problem with that one right now. But we've done some exploration on that and have a much better understanding. And from our perspective, the BMKP2 surface is the best one to work with right now to answer questions about dissociation. Now, let's have a look at these potentials, because this gets back to, does it matter what hits the hydrogen molecule? So in our top left labeled A, that is a helium atom in H2. This is a collinear cut. So you have your hydrogen molecule, and your hydrogen molecule bond length is R2, that's the target molecule. You have the other one coming at distance R1 away, the horizontal axis. And what you see in that first one, if you look at the shape of those negative contours, is as the helium approaches, it's almost like the hydrogen molecule sort of cringes. You know, it's a repulsive sort of interaction. Now, if we take H2 and H2, sorry, let me do H plus H2 first. Okay, H plus H2, hydrogen atom has one electron. It's open shell, unlike helium, which has its 1s shell closed. So, and the thing about unpaired electrons in chemistry is they really like electron density, you know. So as a hydrogen atom approaches H2, you get an attractive interaction. And you can see that as the bottom of the well sort of curves around the corner a bit. So as a hydrogen atom approaches an H2 molecule, it kind of stretches. Now, H2, if we have H2 in this ground vibrational state, and our target H2, frame C, shows essentially repulsive interaction. And that was the basis of a lot of arguments in the literature. So like, well, we don't have good numbers for H2 yet, but we have numbers for helium H2. Why don't we just patch them up a bit? It's the same type of interaction. Oh, wait a minute. Okay, D, H2. Now the approaching hydrogen molecule is stretched to its outer turning point of E equals 12. So this hydrogen molecule is basically experiencing the end atom and not the two atoms. And that's much more like an open shell interaction. So it's not going to be a simple matter of taking some existing data and kind of patching it up. So, yes?
I don't understand what's the difference between C and D.
C and D, they're both H2. The first one is the collider H2 is in its ground vibrational rotational state. So it's fairly compact. So as it approaches, it's seeing both hydrogen atoms in that molecule and the paired shell, you know, the closed shell. This one, the collider is stretched to its outer turning point for the V equals 12. So as it approaches, it's seeing this hydrogen atom, this other one way over here, might as well not be there. So that gives that a sort of attractive interaction. Are there any other questions? Okay, so we want to get some information about what happens in collisions. Quantum methods. I mentioned earlier, you know, there's quantum calculations for VJ states up to roughly 1 eV. And that's because the size of a quantum calculation scales sharply to like about the 5th power of energy. So double the energy, your calculation is 32 times as big. So right now, if you look around, you find that there's quantum calculations, full dimensional quantum calculations, that are up to about 2 electron volts. You know, that's total energy. So that's the energy, internal energy of the molecule involved and the collisional energy. There are restricted dimensionality calculations for higher energies, but they don't help you much with full dimensional stuff. Well, we can't get away with this low VJ states if we want to model the interstellar medium. You know, when we start throwing in the quasi-bound states, we're getting up close to 5 electron volts. Right now, we can't do that quantum mechanically. So we're going to use a classical approach. So this is back to the proof of concept in the 1930s. We're going to use what's known as the Quasy Classical trajectory method. What happens is we initialize a molecule to have internal energy corresponding precisely to a VJ state. Then we forget about quantum mechanics. We start the collider way over here. If it's a molecule, it has its own VJ state. And we let the collision evolve classically. Now, the really nice thing about doing it classically is you can keep track of which atom is which. So you let it progress classically, and then we get to the rub of QCT, which is what do you do at the end? So more about that. Okay, so these are some quasi-classical trajectory results. Okay, a little slight difference in labeling here. We have frame C. That is what happens when a helium hits H2. This, I believe, is for roughly 1/10 of a heart rate. And so helium, when helium hits H2, you kind of excite rotation. Rotation is the horizontal axis, vibration is the vertical axis. If you go to frames A and B, that is hydrogen hitting H2. And because it's classical calculation, we can know whether a switcheroo of the partners has happened. So the upper one is for no swapping, and the bottom one is for swapping swapping one of the H's, so the H plus H2 exchange reaction. What we notice in this particular energy is that exchange is highly favored. The barrier height to exchange is about 1/4 of an electron volt. And that dashed line, that dark dashed line, sort of indicates the boundary of the energy envelope in BJ space. So what we see in both the exchange and non-exchange cases is a lot of trajectory results are sort of spanning the whole range of the envelope. When we generated this diagram, we didn't put all the trajectories on. It would have been a solid mass if we did. H2 was really interesting. We looked at one of the products, the target product. Similar pattern to helium H2, but considerably dampened. Well, one of the ways to interpret that is that unlike helium, which is kind of like almost like a hard sphere, a hydrogen molecule hitting another hydrogen molecule, that's kind of spongy. So it dampens the energy transfer. So this meant that there was no way we're going to take existing data and try to create H2 cross sections or rate coefficients. Okay, in this diagram, we're looking at what's known as an integral cross section. I'll talk a little bit more about how we calculate cross sections in a few minutes. Integral cross section as a function of total collision energy, of the collision energy. And there are 4 curves on this diagram. Triangles are helium. So we see that the top line That's rotational excitation from V equals 0, J equals 0 to V equals 0, J equals 2. So just straight rotational excitation. Smallest energy gap for a transition. And helium H2 is really good at exciting it. That kind of jives with the previous figure. Then, slightly below that, we have the H200 as the collider. Pretty similar pattern. Down below, we have the uppermost curve going from 0, 0 to 0, 2 is for non-reactive hydrogen. And then the very bottom, it's exchange. Exchange is pretty weak when it comes to this. That's because in the interaction potential, when you look at H hitting H2, they kind of interact a fair bit and they forget where they came from. So in an exchange reaction, you're going all over the place. There's almost no memory of the initial state. There's a bit of memory if reaction doesn't occur. Now let's look at vibrational excitation. So we're going to go from 0, 0 to 1, 0 for the hydrogen molecule. Now, our non-reactive hydrogen is really taking it away on the vibrational excitation. Our hydrogen molecule, this one's kind of interesting because it comes up here and then it sort of flattens out. It's probably flattening out because other channels are becoming accessible as the translational energy goes up. But the other thing to note is it rises from 0 at the same position that the H atom as the collider rises from 0. Helium H2, we don't really noticeably rise from threshold until we have considerably more collision energy in the system than is required to, for the energetic transition. That is a threshold elevation effect. And we see that a lot with closed shell colliders and molecules. If the closed shell molecule is an atom, so a noble gas atom hitting a hydrogen molecule. And then we don't see all that much for exchange, again, because there's also stuff going on with other channels. It's filling that energy envelope. Now, dissociation. Dissociation is really important in the cooling of interstellar shocks because the densities are low enough that those atoms are not going to come together and form a new H2 molecule. So once you put in that dissociation energy of roughly almost 4.5 electron volts, that energy is lost forever from the system. So it's an important cooling mechanism. Okay, we find that hydrogen atoms are the most effective collider. In fact, one hydrogen atom, at 2000 Kelvin, one hydrogen atom is as effective as a mole of helium atoms. They differ by more than 23 orders of magnitude. In the rate coefficient at 2000 Kelvin. And we see that with our helium because we've got this threshold elevation. To dissociate a hydrogen molecule from 0, 0 with a helium collider takes 2.5 times the energetic requirement for dissociation. Basically, it's such a repulsive interaction, you kind of got to give it a karate chop. And then H2, the exciting thing about H2 as the collider is there's no threshold elevation. It's not as efficient as the hydrogen atom, but it's still playing a role there. Okay. Now, so basically my old modus operandi is I run trajectories and I get cross sections, and then I can get rate coefficients. But to get a rate coefficient, you're kind of assuming a temperature, and that's not always valid. So that's where the cross-section data is important. You can take any energy or velocity distribution and create the type of rate coefficient you need for the context. Okay, so we do something called stratified sampling, and this is, we don't want to waste a lot of computational effort. So we start off with our hydrogen molecule here, and we basically Monte Carlo select over an area. That's the first impact parameter strata. If interesting things are happening, we go to the next strata, and the next strata, and the next strata. I'm now doing some calculations right now with H2 in highly excited vibrational states. I'm now going out to about 15 Bohr, whereas when I was working with 0, 0, 3 or 4 Bohr would do it. So you just keep doing that, and because you know these areas, you could use that area as a weighting factor to calculate the cross section. So we just keep moving outward. Everything else about our collisions we Monte Carlo select using a robust random number generator, and we get our cross sections. If we want temperature dependent rate coefficients or rate coefficients at a particular temperature, we convolve that with the Boltzmann distribution. Now, we like error bars. And sometimes we're dealing with rare events. So when I was a doctoral student, I wound up working closely with Peter Martin, and we spent a lot of time contemplating the zeroness of zero. Like, you know, is the cross-section really zero, or is it because we haven't looked hard enough? So we had to get an error bar on a zero, and this is how you do it. You'll notice when the probabilities are large, this will reduce to binomial distribution. But when you've got rare events, those other terms become really important. So basically for each stratum, you count the number of events, little ni, leading to the process of interest. You've got the total number of events in that stratum. That gives you a probability. You've got the area of the stratum. You add it up until it converges. And you put an error bar on it. Now, this solid dark line, that represents what's sometimes called an excitation function. Again, earlier in my work, there was quite a bit of literature on forms for the excitation function. We found the forms didn't really work terribly well, so we don't use them. Basically, what we do is we calculate cross sections on a fairly dense energy grid, and then we have to convolve that with the Boltzmann distribution. So I have Boltzmann distributions at various temperatures, and the thing to note is the lower the temperature, the more important are those cross sections in the threshold region. So you really got to get your region, your threshold region nailed. Anyway, you convolve them and you can get a state-specific rate coefficient at the temperature of interest. Now, the way we do that is we basically go dot to dot on our excitation function. We assume that it's piecewise linear. And that also has the advantage that we can rigorously propagate the uncertainties. So we can generate rate coefficients with error bars. And we have to pay very, very close attention to the threshold region. Now with helium H2, with threshold elevation, it was kind of tricky when we started working with H2, we did some restricted dimensionality studies, which assured us that the thresholds were energetic. As soon as there was enough energy in the system, the process could occur. When we went to full 3D, that meant that we had to nail it. The other thing is if we're going to model interstellar shocks, we have to pay attention to detail balance, i.e., at equilibrium, the forward rate equals the backward rate. You can also think about that in terms of microscopic reversibility. You could run a trajectory backwards and get back to your initial state. So we require in our sets of rate coefficients that this is obeyed. Now, fitting the results. We start precisely in a quantum state. We can wind up anywhere at the end of the trajectory. So we have to bin. If we're dealing with one H2 molecule at the end, then we have a two-dimensional bin. If we're dealing with H2, we have to consider the quantum states of both molecules. So we've got a V and J for each molecule. We've got a four-dimensional final bin. Now, this is where microscopic reversibility kind of breaks down with QCT, because your final state's anywhere in the bin, but you start it precisely in the middle. So if you were to run trajectories from the final state to the initial state of interest, you would not expect those two to match, because you're going from this state to a range of stuff here, or you're going from this state to a range of stuff over here. So you can't assume it's going to automatically be obeyed. The other thing is there's a vast array of literature about how quasi-classical trajectories are hot. And this is a paper that I did as a graduate, well, after I finished my PhD, but the work was mostly done during my PhD. Peter Martin and Bill Keogh and I had a look at some of the binning methods. And basically what happens, here's your grid, here's your trajectory result. So under our binning method, it's sort of like it's in this bin, we assign it to that bin. There are other binning methods that were older, that were developed in the context of highly constrained computational resources. They wanted to get as much information as possible. So one technique was to construct a unit bin around this, and then say, okay, it contributes this much to this one, this much to that one, that one, that one. That actually made the problem worse. So, about the same time, quantum results are coming out. Really good full-dimensional quantum on H plus H2. That's the dark solid line. We found our direct cross-sections, conventional histogram method, were shifted slightly. The smooth one, that's where they have the overlap with the bins and stuff. That one made it worse. We looked at trajectories in the other direction and then applied detailed balance. We got very, very good agreement with the quantum results for all the states that were available. That was very satisfying, because it meant that probably our higher energy ones were okay too. So we moved forward to a complete set. I realize I'm getting close to the end of my time here. We came up with a complete set that obeyed detailed balance. We parameterized them with temperature. Peter developed a functional form that obeyed detailed balance. And we combined all of this and we published the numbers in Astrophysical Journal and how we did it and what we considered in doing it in the Journal of Chemical Physics. Once you have that complete set of rate coefficients, you can do master equation calculations. That was the next PhD student with Peter, David Schwartz. We can also test scaling walls. And there's a huge number out there. Like there's a paper by Sternberg and Delgado that has dozens of them, and they don't work. but we had a set of numbers that said they don't work. But they're still widely used. And more recently, all of a sudden the energy gap law has come to the fore again. It doesn't work either. So how are we going to get H2H2? Okay, not much quantum out there, restricted dimensionality. That's good for the restricted dimensionality, but it doesn't get you to full 3D space. Needed a full dimensional quantum study. That was my first sabbatical. I ran into David Clary at a conference and said, nobody's done this. What about it? I wound up going there on my sabbatical and doing it with Clary and Probevna. We had hoped that we might see the same thing we saw for H2. We didn't. So the barely in the box problem is much more accentuated for a 4-dimensional box than it is for a 2-dimensional box. We tried looking at stuff the other way. No, doesn't get us to where we need to be. So I think we're stuck with waiting for more quantum calculations to get state to state for H2 plus H2. There is a method out there called Gaussian cross-sections. There's various applications of it. The one that's being proposed when you have more than 2 quantum numbers is to sort of use a Gaussian weighting function based on energy. So in the 2D case, it kind of looks like this. You know, the stuff that's on the iso air gets weighted heavily. The stuff at the low VJN doesn't get weighted much. Some of the stuff at the high VJN. That doesn't solve the barely in the box problem. You can get trajectory results down here that don't have the energy of the state, but give you a non-zero cross-section. And of course, that affects everything else that's calculated from that cross-section. So it doesn't get you there, but I'm kind of finding it a case of, here's a nice model, but it doesn't work. You know, but a lot of people are using it. Where we are now, we're looking at dissociation. Nice thing about dissociation, we don't have to be in. But we get threshold behavior. Now, this is where the zeroness of zero matters. Because if we get a zero cross-section, we could estimate if the cross-section was the size of that error bar, how big a batch would we need to have a 50% chance of seeing it? And in some cases, you need millions. So we realized that we were running through our recursive random number generator, so we had to switch to the Mersenne twister. But we systematically went at it, and we got some state-specific dissociative rate coefficients, which were published in an astrophysical journal. So now we're working on some higher energy states, and we're sort of focused on that right now. To go forward, we need better potentials. Okay, we need to resolve the issues with the H2H2 potential, which means we also need improved quantum calculations. Balakrishna is really pushing the energy envelope on H2H2 quantum calculations. There's also some really exciting stuff happening around new methods to develop potentials. The gas phase chemical physics group at Argonne, I mean, they're more interested in consistent thermodynamic tables, but to get the numbers they need to develop new techniques for potential energy surfaces. And we need to deal with the situation where electrons do not belong to particular nuclei. They have some techniques that are not computationally tractable, but they're getting bigger and bigger computers all the time. So in the meantime, I'm just looking at CID. People, okay, people and computers, okay. Nice thing about being a small university, I have very little competition for cycles. We've had a high-performance computing center and an enhanced high-performance computing center at UNBC. They're now defunct, but the meteorologists and the fluid dynamicists were the main users of the cycles. I had my own queues set up. Whenever there was other queues were empty, my stuff ran. I was invisible to the other users, but I soaked up a lot of cycles. I'm taking the same approach with our new computer, which has come to us by the Hawkeye Institute, which is interested in glaciers and ice, snow and ice. So I'm dealing with the glacier modelers, but I'm still invisible to them, and I'm still getting lots of cycles. We don't have a doctoral program, but I've had a series of graduate students. I've also had interns from the Indian Institute of Technology. Very good experience with those. I've had a series of honors students, some of whom are related to each other. Seamus and Brendan are nephew and uncle. Found that out when I was almost done with Seamus's thesis. I've had a research associate and a postdoctoral fellow, and I've had funding from NSERC and the Science Council of BC. Thank you for your attention.
Thanks a lot, Margot. Let's open it up for questions in the room or online. Questions? Maybe I can kick us off. So you mentioned a few slides ago that you don't have these binning problems. You don't have to do the binning problem for, I think, the dissociation.
Yeah.
And so why is there that difference versus the other reactions we're studying? Does it have to do with the potential?
Well, basically, as you approach the dissociation limit, you approach the continuum. So you don't assign a quantum state.
I see.
So you basically set if they're more than 20 Bohr apart, they are dissociated. Basically at the end of the trajectory, in the 4-atom case, you look for the closest pair of atoms. And then you calculate their angular momentum around each other, which allows you to calculate an effective potential. And then you do an inverse quadrature in that potential to get the quasi-classical vibrational quantum number. And then you repeat the same thing as the other 2 atoms. If there's no minimum in the effective potential, it's dissociated. So dissociation is pretty unambiguous. Though we have found that we have to start much further out, than if we're just looking at energy transfer.
I see that Juna has a hand up online. Go ahead, Juna.
Yeah, thank you, Margot, and thank you for visiting us at CITA. Sorry I can't be there in the room today. I guess I have maybe a phenomenological question, I guess, is, when I think about where these problems really, and these calculations that you're doing, when I think about the place where I really want to understand the answer, of course, it's the interstellar medium locally, but I also think about high redshift star formation and molecular cooling and what the sort of first stars might look like. And I just wonder, if, in your mind, where do the physical conditions get sufficiently wacky and interesting that some of these calculations really need to sort of go out the window or at least have significant revisions? In other words, do you think that in the era of reionization or in sort of first stars, do you think that some of the new observations are going to start to really push these calculations to their limits?
Well, these are all in the ground electronic state. So once you get electronic excitation, it becomes much, much more complicated. The first electronically excited potential for H plus H2 intersects at about 2/3 of the way to the dissociation limit. So there's a whole body of literature on surface crossing, how you get the coupling between the surfaces and stuff like that. So there's lots of contexts where this simply would not apply. We have to deal with something that's fairly cold where there is not ionization. Ionization is kind of the ultimate in electronic excitation.
Right, but in sort of those first stars where you haven't really, you have heat, but you don't really have the same kind of ionizing flux yet, right?
But then you have to get hydrogen molecules.
Yeah.
And the 3-body recombination rate for basically, to form a hydrogen molecule in the gas phase, you have to have a 3rd body that removes the energy. Otherwise, it's just, So the mechanisms that are believed to be important in the early universe tend to be the ones that involve electron attachment and stuff. So you have to move electrons around to get those first hydrogen molecules. Once you've got the hydrogen molecules, then you can start processing radiation and emitting radiation, processing translational energy into radiative energy and cooling stuff, and maybe getting the right density for gravity to win.
Yeah. I guess I was just asking whether you thought that any upcoming observations were really going to constrain any of these calculations in an interesting way.
Not perhaps the ones that I do, but I think they're going to give us a much better sense of what other electronic states are going to be important. I'm in trouble keeping up with the amount of stuff that's coming out lately. But, I'm watching previous assumptions kind of being blown out of the water. So I wouldn't be surprised if that happens here too.
Thank you.
Okay, let's go to Peter online as well.
Hi, Margot.
Hi.
Sorry that I'm not there today. I'm thinking of real interstellar gases,
Yes.
and I'm wondering if you've done back of the envelope assessments of how long or how accurately or how long do you have to know the H2 plus H2 cross sections, because once you're able to create in the interstellar medium some hydrogen atoms in the gas, maybe it's a minority compared to what there is.
Oh, they're just going to take over.
Then it will take over. So
yeah. So that's why sorry.
Yeah. Well, so there's two ways to get the hydrogen, perhaps, maybe more. One is the collisional dissociation that you have up on this slide. And the other is to just have some leftover that you've not converted everything into hydrogen molecules in the first place.
Mm-hmm.
Then, as you say, the hydrogen atom plus H2 could take over, and maybe after all of our efforts, we don't need really to know as much about H2 plus H2 as we thought we did. I think we have to know about it from theoretical point of view and just in quantum physics, but for the practical master equation evolutions and so on, maybe not. That's a question mark.
Yeah, well, I think, the stuff I've looked at so far, once you have hydrogen atoms, the contribution of H2 plus H2 to energy transfer is pretty negligible.
Yeah.
So it's kind of like, okay, I can't get it classically, they're inching towards it quantum mechanically. I'm going to move on and look at the production of H atoms from H2 plus H2.
Yeah, because that might be the key process in understanding the master equation evolution.
Yeah.
Yeah.
You can put in sort of model numbers and do sensitivity analysis and stuff. But I get to recruit a graduate student with the adequate math background.
Okay, well, thank you for the broad coverage in your talk.
Thank you. Will you be here tomorrow?
I'm hoping to, yes.
Okay, good.
Okay, well, I think we better leave it here, but we will move upstairs to the lounge for more discussion over snacks. Margot's with us until Tuesday if you'd like to chat. So thanks again for the great time.